I want to apologize for this late change in timing, and unfortunately in WebEx, when I change time, I have to change the link, etc. At least I haven't figured out how to do it without changing the link. So sorry about that, but this is just for today. There is a slot change, and I don't know how many, I mean, I don't even know if the e-slot instructors are changing, etc. But this is the institute calendar, so best to follow that. Okay, so what we were doing last time was we were discussing the density operator in general. Of course, today I want to specifically discuss also the qubit density operator. But in general, for density operators, we were discussing the so-called Schrodinger-Houston-Josa theorem, Wutter's theorem, which talks about the non-uniqueness of the ensemble description of a density operator. And it says that two ensembles that is EI psi I and UJ phi j represent the same density operator if and only if they are related like this. So I said that this set has some m elements, this set has some n elements, right? And we said that P has to be whichever is the larger of the two with 0 vectors appended to the shorter set. Okay. Sorry, I think the other way around. This had n and this had n. Okay. Just doesn't matter. I don't want to change from one class to the other. Yeah. So if and only if they're related like this. So basically, one is relating the unnormalized versions of psi I and phi I, the weight coming from the corresponding probability distributions. And the key point is that these coefficients have to be drawn from a unitary matrix. You call this some U is a P cross P unitary matrix. Okay, and P is whichever is the larger of N and M. Okay, so when do we say that two ensembles correspond to the same density matrix? That means there's a single row such that it can be expanded as one set of pure state projections, psi i's, and another set of pure state projections, phi j. Right? And like I said, this is a very important idea because you don't quite have this idea for pure states, right? And that's why the pure state description is a much more clear-cut description of the system. There is really no uncertainty in the pure state description, right? Like we discussed, we can talk about a purity, and the purity then is related to something called the entropy, right? So in some sense, the mixedness of the state has various inherent uncertainties associated with it, and this is one such, right? So if I want to view this density matrix as a convex sum of pure states, there is no unique way to do that. There are multiple ways of doing it, right? Of course, there's a constraint that these multiple ways must be related by a unitary transformation. Okay, so we proved one direction of this, right? So we showed last time, right, that if, okay, so let me call these two equations as something. So let me call this equation as 1, and let me call this equation as 2. Okay, so last time we proved that if 1 holds, then 2 holds, right? In the sense, if these two are related by uij, then we simply took these two sums. I mean, we took this sum, substituted for one here, and then we showed this, right? Like I said, the somewhat more laborious way, it's not hard really. It's more a question of understanding, for example, the unitarity property and applying it correctly, right? So the converse, which is if 2 holds, then there exists a unitary matrix U such that 1 holds, right? So this, to prove this, I'm just going to indicate the outline and will leave the details for you to do in an assignment. Okay. So there exists a U such that 1 holds. So how do we show this? The route to showing this, the main proof strategy here is to go to the diagonal representation. Okay. So we have just said that there are two equivalent pure state descriptions. Now, in general, a density matrix also admits a diagonal representation like this, right? So then the trick is actually to go like this. You have this description, which is the psi I, okay? So you relate that to this. In fact, you relate these two sets, and then you relate similarly this set, with the QJs, phi j's, okay? And hence you end up with a relation between these two ensembles, these two pure sets of pure states and the probabilities. Okay, so what we can show in fact is that there is a unitary that relates these two, there is another unitary that relates these two, and then note that if V and W are unitary, if I write down a matrix U, which is I think doesn't matter, but let me just write it the way it is supposed to be, which is I think okay, VW dagger. Okay, what can you say about U? Can you check? What can you say about U? Which is the product of two unitary matrices essentially. Doesn't matter that there's a dagger there, but I just put it because that's what will turn out in the proof.
Will be unitary.
Yes, why? Can you quickly say why?
I just take the dagger of U and multiply both. So I get V W dagger into W V dagger.
Correct. Exactly. Good. So if I do U dagger U, then that interchanges the order, right? First, so that gives me W V dagger, V W dagger. I think I already covered this when I discussed unitary matrices. I'm not sure, but since these are both unitary, this is identity. And if I have U dagger, then that's also V W dagger. The dagger again interchanges the order. So I have W V dagger. And of course, this is identity. So this is indeed a unitary matrix. Okay, so this is the essence of the proof. The details are slightly, I mean, it just requires careful working out of things. The key reason why these two turn out to be unitary is related to the fact that there is one description of the state which is in terms of orthonormal states. Okay, while these states are normalized, they are not orthogonal, but because there is one description which is always in terms of linearly independent states or orthogonal states, then that gives rise to the fact that these things can be related by unitaries. Okay, but once again I repeat, this is not the same as diagonalization. In if I'm in a non-diagonal representation, in some bases I will have off-diagonal terms, right? I will have non-diagonal terms. But this is truly an ensemble, an expansion in terms of a particular set of pure states, another expansion in terms of a particular set of pure states, and they are related by a unitary transformation U of this form. Okay? So, questions? Too early in the morning to be discussing ensemble description of density matrices, I suppose. Okay, so the next thing I want to do is to focus on the qubit case, okay? Because for qubits, we had a nice geometric description of the pure state. Right now, I'm going to constantly keep talking about pure versus mixed states, okay? And I hope you understand.
Ma'am, I have a question.
Yeah.
How do you know that U is V W dagger and not any other combination?
Oh, because I've worked out the proof. You will show that.
Okay.
And
Okay.
if I'm wrong, you will also show I'm wrong. Okay. I mean, it is some combination of V and W. I'm just saying, see, it is a directionality thing, right? If I go from psi to E, so let's say this is how it is, okay? So let's say that the arrow marks go like this. So there is a V that takes me from the psi description to the EI description. There's a W that takes me from the phi to the E. Then what takes me from psi to phi? One of these two will have to be the adjoint unitary. Do you understand? If W is the unitary which is taking me this way, the unitary that will take me this way is W dagger. Right? Because unitary is always a invertible transformation and the inverse is the adjoint. Right?
Yes, ma'am. I got it.
So yeah, so one of these matrices will have, you'll have to have the adjoint there. Okay? Yeah. Okay, good. So like I said, yeah, this is the broad proof idea. I've already laid it out. I just want you to work out the proof yourself in the assignment so that you get some practice of, you know, doing these pesky sums and taking, you know, showing the unitarity property and things like that. Okay? Making use of the unitarity property rather. Okay. So there are some nice things we can observe about the qubit density operator. Okay. So what do I mean by the qubit density operator? So if I take a two-dimensional system, right? So if I write down a density matrix for a two-dimensional quantum system, right? We already saw some examples of writing down these density matrices. So they're all 2 cross 2 complex matrices, right? The formal way would be to say that this belongs to this, which I wrote down sometime very early in the course when I was describing linear vector spaces and so on, right? What is this M 2 cross 2? I think I wrote this as M 2 cross 2 of C. This is actually a linear vector space, right? It's a complex linear vector space of 2 cross 2 complex matrices. And by complex, I mean that the entries are complex, right? We already showed that this is a vector space, right? It satisfies the properties. We even identified a basis for it. Okay. So what is the basis that we identified for it? Yes. Quick.
1 0 0 0 0 1 0 0 0 0 1 0 and
Yeah. So first of all, note that this is a what dimensional vector space? What is the dimensionality of this vector space? 4. Yeah. So this is a 4-dimensional linear vector space. So the basis will require 4 elements, right? So this is the basis that we wrote down. It's a basis of matrices like this, right? And so of course, every row can be written as some A1000 plus B0100 plus C, oops, Now, where A, B, C, D are all complex. Okay. Now, this is fine, but instead of this description, there is a more interesting description in terms of a different basis, which actually brings out the properties of the density matrix much more nicely, particularly for qubits, right? Now, if this is a basis, there must be some notion. The question is this an orthonormal basis? Okay. But if you have to answer this question, then you have to have a notion of inner product, right? So what would be a valid inner product for this system, this set of complex 2x2 matrices, right? So one way to get an inner product, so remember the entries are all matrices now, okay? So if I'm going to write an inner product like this, I put a comma here, not a ket, because these are not really vectors, right? So just to distinguish a little bit for ourselves so that we don't get confused. But I could equally well put this as well, right? So what would be a good inner product for this would be to take, so how do I take two matrices and get a number out of it becomes the question, right? Yes, you've all done your assignment. Yes or no? So what is a good inner product for this?
The trace,
Correct. Trace of what?
the product of A and B dagger.
Which way? So you always take the complex conjugate or the adjoint of the one on the left. That's what physicists do, mathematicians do it the other way. But so this is an inner product. Okay. Assignment 1, question 2. What part? You guys have done it or not? Yeah, exactly. Okay, fine. So question 2.4, right? You showed that you take this inner product, and I even gave a name for it. I said it's a Hilbert-Schmidt inner product. And first of all, of course, this is a check that you can do, which is not there in the assignment. Check that this set of matrices, no, this. So let me call this as B, okay, this basis. So check that B satisfies the, rather check that B is indeed an orthonormal basis as per this inner product. Okay, which means for take each of these pairs of these matrices and show that trace of A dagger B actually vanishes, right? And that the trace of A dagger A itself should be 1, right? So this is what is called the Hilbert-Schmidt inner product. Okay, for a pair of matrices, because they form a linear vector space. What is more, they form a Hilbert space. They are linear vector space with an inner product. Okay, so we can define the notion of an orthonormal basis here, and so this simple basis is also an orthonormal basis. But the basis that we are interested in is the basis that you guys showed in question 2 of the assignment, which is the Pauli basis. Okay, so we are interested in this set of 4 matrices, which is basically identity sigma x, sigma y, sigma z, right? And you showed that this forms an orthonormal basis, but I had asked you that what is missing is a certain normalization. So what is the normalization that you had to put in?
1/√2.
Exactly, good. So this itself is a set of mutually orthogonal matrices. Orthogonal in the sense that, so what I'm going to do now is to have this notation where I denote this as sigma I. Okay, so sigma I I going from I0, 1, 2, 3, okay? And yeah, so this is what I will call as the Pauli basis. And the idea is that sigma 0 is identity, sigma 1 is sigma x. Doesn't quite matter what is what, but I'm just to write down things more simply. It's good to use the index notation. And the point is trace of sigma I dagger is the same as sigma I for all of these. So trace of sigma I sigma j is going to be delta ij, but not quite, right? It's actually what? What's the factor here?
2.
It's 2 delta ij, because if I take the square of any of these matrices with, if I take sigma I, the square is identity, and trace of the identity matrix is 2, right? So they are mutually orthogonal, but they're not yet normalized. So if I take sigma I by root 2, then this becomes an orthonormal basis. This forms an orthonormal basis, I going from 0 to 3, right? So this is a set of 4 matrices that spans the space of 2 cross 2 matrices. So then, of course, I should be able to write every density matrix, qubit density matrix, as R0 sigma 0 plus R1 sigma 1 plus R2 sigma 2 plus R3 sigma 3. You see, it really doesn't matter which sigma is 1, 2, 3. It just matters that there is a sigma 0 which you distinguish because that's the identity, and there is the remaining 3 sigmas. Okay. Now, what can you say about R0, R1, R2, R3 for rho to satisfy the properties of a density matrix? Okay, so what are the properties that you can identify for? So first note that trace rho must be 1, right? This is one property. So what does this imply? Quick, what does this tell me about R0, R1, R2, R3?
R0 should be half.
Okay, good. So R0 should be half. Actually, what I should have done is to put the half already. So let me write this as half of this, okay? Because we know that there is a normalization factor there of 1 over root 2 anyway, but I would like to put a half here. And the reason is very clear, because then R0 should be 1, correct? I hope everybody sees that, because if I take trace of rho, then sigma 0 is nothing but identity. So maybe I can just write this as identity itself. Okay. And this is the only trace giving part of this, right? The rest are traceless. This part is completely traceless. Pauli matrices all have trace 0, right? So then this tells me that R0 must be 1. Okay. So next, let's go step by step. So let's say that rho dagger is the same as rho, right? It's Hermitian. So what does that imply? We've already fixed R0. That's it. R0 is 1, fixed. Now what about R1, R2, R3? What can you say about them?
Must be real.
So because sigma 1, sigma 2, sigma 3 themselves are Hermitian, correct? So if rho dagger must be the same as rho, then I must have R1 star sigma 1 plus R2 star sigma 2 plus R3 star sigma 3. There's also the half, okay. Okay, let me write down what it implies and then argue it out quickly. So this implies that R1, R2, R3 must all belong to the reals, which means I can write down a vector, and now I put a typical vector sign of a 3-dimensional real vector space, right? R vector with entries R1, R2, R3, which is essentially a vector in my usual 3-dimensional real space, I associated 1 with X, 2 with Y, and 3 with Z for a reason. So now you see things get interesting. I can mark this out on a 3-dimensional vector space with a vector. Okay? But there are more constraints. So let's look at those. But why does this happen? Well, you just have to take the adjoint here, equate the two. Now, when I equate any such sum like this, it's not, of course, obvious that you can take the coefficients and equate them, but in this case, you can. Why? Because the expansion is in terms of a set of orthonormal objects, linearly independent objects. So when I equate two sums like that of linearly independent objects or orthogonal objects, then you can do a quick check. If you take an inner product either way, then you will notice that these coefficients must match. Okay, I hope what I just said makes sense. Think about it. Try and show this. Okay, so prove this. Convince yourselves that this is true. Okay. All right. Now, what else? See, this is not all right. We said that rho has to be positive semi-definite. Correct? Is that guaranteed? So is it guaranteed that if I take the expectation value of rho with respect to an arbitrary state psi, that it is always going to be greater than or equal to 0? Okay. The other question is, we know already that, so while we think about this, so we have already this idea that if I take this 3D real space, okay, then we already know that we have a description of pure states on this. Yes? How do we describe pure states in this picture? Are people still around? Not around?
In terms of Bloch sphere,
Exactly. So we have the Bloch sphere description, right? So we know that if I draw a unit sphere means what? If I put an R vector here, right? And if I mark out a unit sphere, which means mod R is 1, then that is the so-called Bloch Poincare sphere. And that represents all qubit pure states, right? So any point on the surface of the sphere marks out a pure state for me. I can write it in a density matrix form like this. But the point is that every point on the surface of the sphere marks out a density matrix for me. Okay? So what I can simply do is to take this condition, which is trace rho squared, okay, which says that trace rho squared, yes, what do we know about pure versus mixed in terms of trace rho squared?
For pure, it will be same as trace of rho.
Yeah, if it's mixed, if it is mixed, what happens?
less than 1.
It will be strictly less than 1, right? So then because of this, what happens? We get, can you quickly work out what this implies? And then we'll come back to the positivity condition. So if I impose
Points
this,
inside this.
exactly, you will get points inside the sphere, but please just work it out. I'll just give you a few minutes to work this out, okay? Because it's also a useful exercise with the Pauli matrices and so on. So this is the fourth property I'm invoking, okay? So what is rho squared? Rho squared becomes 1 by 4 identity plus R1 sigma 1 plus R2 sigma 2 plus R3 sigma 3 the whole squared, right? The question is, which are the parts of this which have trace, right? That's the clever way to think about it. Of course, you're going to have the identity term. Then you're going to have the R1 squared term, which comes in with sigma 1 squared. Sigma 1 squared is identity. R2 squared will come with sigma 2 squared. R3 squared will come with sigma 3 squared, right? So when I write down trace rho squared, I'm going to get 1 by 4 trace 1 plus R1 squared plus R2 squared plus R3 squared times identity plus are there other terms which are going to contribute to the trace?
The pairwise products will be 0.
The trace of the pairwise products is 0. We already showed that in your assignment. What about identity times sigma 1, identity times sigma 2, and so on?
That is also 0, because no polymer trace is a trace.
Indeed, yes. So I basically have a whole bunch of terms, but the point is all of them have single Pauli matrices. So all of them have trace 0, right? So now if this is the left hand side of this inequality that I'm evaluating, okay? And so this is simply going to become 1 by 4, 1 plus, I'm going to write this as R dot R, okay? This part is simply the real vector space, real 3D space. It's just the dot product of the two vectors times trace of identity, but trace of identity is 2. So I just have half 1 plus R dot R, okay? And the inequality tells me that half 1 plus R dot R is less than 1, strictly less than 1 for a mixed state, okay? In general, it's less than or equal to 1, but for a mixed state, which is not strictly not a pure state, this is strictly less than 1. So then that tells me that R dot R, which is nothing but mod R squared, is strictly less than 1 for a state. So then this is the question that someone asked me at the very beginning. What are the points in the inside of the sphere, right? Now you know the answer. So when I have a Bloch sphere description and I write and I map the qubit states to states of the 3D real vector space, then we said that they're all, points on the surface of the sphere. So what lives on the surface of the sphere is pure states. What is in the interior, here, etc., are all mixed states. So the interior is all mixed states. So now this description is complete. So actually this sphere, the complete sphere, represents the complete state space. And I say beyond state space, right? It includes a complete description of a two-level quantum system. The points on the surface are the pure states or your state vectors, the points on the inside. And now this should become obvious because if I take a point here, let's say on the z-axis, right? You know that the way we describe it, the ket 0 is sitting here and the ket 1 is sitting here. If I take a convex combination of 0 and 1, right? Now think of this from your knowledge of real vector spaces. If I take a convex combination of this point and this point, you know that I should get some point in the interior of this line, right? That's what your standard real space geometry or real analysis should tell you, right? So it's then obvious that if I take 2 points like this here, then their convex combination should be somewhere in the interior. If any 2 points I take here, their convex combination must be some point in the interior of this. Okay. So because this is basically describing a convex set for you, those of you who have done a bit of convex theory. Anyway, now what is the point at the middle, the origin? Maybe before that, this last point, sorry, I forgot to talk about this, the positivity. So now I'm going to claim that this condition, that mod r be less than 1, right? Mod r squared less than 1, mod r less than 1, is the same condition that also guarantees positivity. Okay? And this is something for you to check out by taking this inner product, taking this expectation value here, right? You know that you have the identity matrix, and you know the rest are Pauli matrices. You know their eigenvalues. Okay, so long as this holds, then this state remains positive. Okay, so this is for you to check. If you're not able to check, I can show this at the beginning of next class. Okay, so please check this. Actually, it should be less than equal to 1. The less than 1 comes strictly when you're talking only about the mixed states. Okay, right. So I hope this is clear now. So what this means is the reason, so this axis that I labeled X, Y, and Z now get much more meaning, right? Because the X-axis in some sense is talking about the component of the density matrix along the sigma X, right? So one way that people write this sometimes is half identity plus Rx sigma X plus Ry sigma Y plus Rz sigma Z. The R1, R2, R3, which forms this R vector, which can also be called Rx, Ry, Rz, is often called the Bloch vector. Associated with rho. So every every single qubit quantum state has a Bloch vector associated with it. If it's a pure state, the Bloch vector is simply a modulus 1 vector. If it's a mixed state, it's some vector which modulus strictly less than 1, right? So this R vector is what is called the Bloch vector associated with a quantum state, right? And so there is a mapping from the states to these Bloch vectors. Okay. So note that unlike the case where you have multiple pure state decompositions and so on, description of a density matrix, this becomes a somewhat better description of the qubit density operator. Like I said, the luxury of the Bloch sphere is not available once we move to higher dimensional systems for various reasons. The geometry of that space is much more complex. But if you just restrict your attention to qubits, then not only do pure states have a nice description, the mixed states also have a nice description in terms of the Bloch vector. So the question I was asking is, what is the origin? So what is the density matrix associated with the origin? Yes? Just the center of the Bloch sphere.
Identity by 2.
Indeed. So center of the Bloch sphere is basically the state, well, Rx, Ry, Rz all vanish, right? So it's a 0, 0, 0 point. right? So the 0, 0, 0 point now becomes, all of these are 0. So all your sigmas go away. So I'm simply left with I by 2. And this state, so the idea is that as you, so the surface live pure states, the interior are mixed states. As you go from the surface down to the interior, you start getting more and more mixed, right? So you're going from pure state, mixed state, and what I'm trying to claim is that as you go further and further inside, your states are getting more and more mixed, which means they have lesser and lesser purity, right? Until you reach the origin, which is, and then you can essentially go no further, right? Because you're symmetric about this. So this is the maximally mixed state. Okay, this is what is called a maximally mixed state. This is the most mixed, the most or the least purity, the state with the least purity, right? One way to see this is to ask what are the pure state descriptions you can write, what are the ensembles you can associate with this density matrix. Can you think of ensembles that you can associate with this density matrix? Can you decompose this in terms of pure states? So what would be ensemble description of this? Think about it geometrically. I'm sitting at the center here. You know several states on the surface, right? You know the 0, you know 1, you know the plus and the minus, you know the plus I and the minus I. So how can you describe this middle point here?
Ma'am, we can write identity as sum of two orthogonal projectors, right? And orthogonal
Exactly.
projectors have the states on the surface, so maybe.
Indeed, excellent. Yeah, that's the point. So I can have, and how many such orthogonal pairs of orthogonal projections can I find? An infinity of them, right? So the point is I can take any diameter of this sphere. So I can take this diameter, for example, and I said the end of the diameter has two orthogonal states, correct? So one way to describe it is as an equal mixture of 0 and 1, right? Because what is this state? So let's write it down. So this, if I write it down as the proper matrix, then it would be half ket 0 bra 0 plus half ket 1 bra 1, right? So what is this in matrix form? This is 1 0 0 0 plus 0 0 0 1, right? We've evaluated these matrices. I hope you remember. So this is nothing but half identity, right? Now you work out another ensemble description. Take an equal mixture of ket plus and ket minus. Okay, so what is this state? Half plus 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 half minus minus. What is this? This also should be half identity. Please check this. But the point is, this is some pair of orthogonal projectors, right? And this is a two-dimensional space. So if I take two orthogonal projectors and sum them, I should get identity. That's the whole completeness relation, right? That if I take a set of elements of an orthonormal basis, I make those projectors and sum them, then that sum gives me identity. I've repeatedly used this relation also in the past. So I can take any such pair of orthogonal states. I can take plus I, which are the eigenstates of the sigma y operator, the minus I, that gives me identity. So I hope I've convinced you that there are infinitely many pure state decompositions of this state. Which means this is a state about which we have pretty much no information. It is a state about which we are maximally uncertain. It is a state of maximum entropy. Normally, when I give you a pure state description, if I tell you that this state could have been 0 with probability 1/4 and 1 with probability 3/4, that physically describes, I mean, that's the physical description of the density matrix, which is 1/4 ket 0 bra 0 plus 3/4 ket 1 bra 1. But that is conveying some information to me. That statement is conveying some information to me, right? It is like in probability theory, if I have a probability distribution which is 1/4, 3/4, that allows me to predict some statistics, right? That gives me some information about this distribution. But if you now tell me that first of all, you have a uniform distribution, which is half and half. But it's not even half and half in this basis. It's half and half in every basis. So this is a state about which you are maximally uncertain. And this plays out in many ways, right? So one, of course, is the fact that the associated probability distribution, no matter which orthonormal basis you write it in, the associated probability distribution is half and half always. It's uniform distribution, which is the distribution with the maximum spread. It is the distribution with the maximum entropy, etc. But also, going back to this Schrodinger-Houston-Jozsa-Wutter's theorem, this is the state which has all possible ensemble descriptions. It has infinitely many ensemble decompositions, right, in terms of this theorem. So this, you will see, will play out very crucially in what we're going to discuss next, which is quantum entanglement. You will find that when I have an entangled state, which is a multi-party quantum state, right, there are two different systems on which I'm describing the state. But if I try to describe such states locally, the individual descriptions will be states like this, which are maximally mixed. Okay. So note that identity operator itself is not a state. Why? Why is the identity operator itself not a valid density operator?
Trace is 2, right?
Correct. So Nilesh is asking me, like, why are you asking such obvious questions?
No. Sorry.
No. But in order to make it a valid density matrix, we have to put this factor of half. And that, of course, comes naturally from the way we have described the density operator in terms of this basis, right? So anyway, this sort of completes what I wanted to say about the qubit density operator. As always, it takes longer than what I think it should. Any questions?
Hello, ma'am.
I hope the Bloch sphere picture is now very clear to you. You should understand every aspect of it, the surface, the interior, the origin, etc. Yeah, sorry, Pratik had a question.
Yes, ma'am. So, as
Yeah.
you said that as we move radially inwards, the state becomes more and more maximally mixed. So, does this also mean that these states loses their uniqueness?
Indeed, yeah. So uniqueness in the convex description of the state, right? So if I'm here, so look at this point, right? I don't know, mark it in red or something. So look at this point. There are obviously several ways of realizing this as a convex sum of points on the surface, right? It's not that it is only this plus this. Correct. I can realize it as this plus this. I can realize it as this plus this. Right? So as I go inside, a point like this can be decomposed as several convex sums of points on the surface. I can pick, these 2 points on the surface can be picked in several ways to make this point. Is that clear?
Yes, ma'am.
Yeah, so that's exactly also the statement of this theorem that we discussed just now, that every density matrix has several pure state descriptions. It just comes out very nicely as a geometric statement for qubits, right? Just a statement about convex. So this is what you would call the convex hull, right? The surface, for those of you who know some convexity theory. But it's just a geometric statement, right? That this point in the interior can have several, you can have several ways of representing this in terms of several pairs of points on the surface.
Thank you, ma'am. And ma'am,
Yeah.
one more question.
Yeah. Pratik, you said you had one more question? I can't hear you.
Hello.
Yeah. Tell me now. I can hear you
Yeah.
now.
So, ma'am, you were using the word ensemble in case of the description of the density operator.
Correct.
So, like, but in this case, we are just looking at a density operator for a single physical system. I mean, like a single qubit. So,
Yes.
how do you represent or explain the part ensemble? I mean, by ensemble, we mean a group or a bunch of qubits, right? But here the description is only for a single qubit. So, how does the word ensemble imply here?
Yeah, good. This is indeed a single qubit system. Okay. But I'm describing states of a single qubit system. And when I describe something as a mixture of ket 0 and ket 1, it is implied when I say mixture that I'm talking now about a collection of qubit states, all of them single qubits, of which a certain fraction can be in 0 and a certain fraction can be in 1.
Okay, so
Of
by
course, the
ensemble,
description
do
is
we
not
mean
of
the
a single.
ensemble of states of the qubit?
Yeah, so there are several physical ways to think about it, right? Either, say, I'm preparing states in a lab. I may not always get the states that I want. So I want to prepare some state in some state like this, right? So maybe an equal superposition of 0 and 1. But maybe with 20% probability, my face flips and it becomes this. So how will I describe my preparation process? Every time I prepare, I'm not guaranteed to have this state. Say that's a state I want to prepare. 20% or 15% of the time, I end up with this state. Okay. So this, as I prepare my states, I will say that I cannot assign a pure state description to this. I cannot simply say this is the plus state. I will say it's a density operator with a large fraction of plus states and a small fraction of minus states. That's one scenario. The other is the measurement scenario, right? I have an equal superposition like this and I measure it. How will I describe the post-measurement state? Unless each time I have to give you a separate description. I have to say this time it was 0, this time it was 1, this time it was 0. But if I want to give a generic description of the state, how do you describe an unbiased coin? You don't say every time you toss it, this is a head, this is a tail. You say 50% chance you will get head, 50% you will get tail. So this is that kind of a description of the state. This is saying that 50% of the time you will get ket 0, 50% of the time you get ket 1. So formally write it as a mixture of ket 0, uniform mixture of ket 0 and ket 1. How do you describe the state of a dice? Every time you roll it, you give a different description. But generically, if I have to describe it as a whole, without each time referring to a roll of the die, I have to say, well, you have a 1/6 probability of getting all these outcomes. That's a die. Right? This is that kind
In
of
this description, we are using the probabilities of their outcome in this case.
Yeah.
Okay.
In the case of measurement, but I'm saying that there could be preparation uncertainty because, like I said, half the time my device or 10% of the time my device will flip the face. Right? Wherever there is some randomness involved here, there could be noise, for example. I'm not sure if I'll have time to get into noise and errors in this course, but there could be noise, right? And when there is noise, again, you get an ensemble description. So wherever there is randomness involved here, where you then have only a statistical description of the state, right? That's where the ensemble picture comes in.
Okay, ma'am.
Yeah, sure. Okay, so I think I will stop here with the description of the qubit density operator. There are a few more aspects of this which we can work out, some interesting properties and all, but I think some of those I will just give in an assignment. Okay. I don't want to discuss more today. People also have class at 9. So I will stop recording and I'll see you all on Monday. Okay.